Welcome back everyone, and today I'd like to wrap our discussion on acids and bases. In one of our previous videos we talked about predicting the position of equilibrium for an acid-base reaction when pK values were given. And now in this video I'd like to talk about the position of equilibrium, but this time without pK values being given. And recall from our last video when we deprotonated the various acids that we were comparing. Once we deprotonated them, meaning losing the hydrogen, they were the acid's respective conjugate bases. So as a quick review again, I have over here, let's say I started off with something like this, an acid-base reaction, and I got something like this. And I noticed that this is basically the same thing as this, but without a hydrogen. This is our acid, and this is our respective conjugate base. So, just as a quick review, I wanted to make sure you guys are still aware of that. Now, with this idea in mind, when we're given an acid-base reaction with no quantitative data, we must focus our attention on bases. Now, to determine which side equilibrium favors and pK values aren't given, we're looking for the more stable base. And I also want you guys to recall is when we're comparing acids and bases, the more acidic a compound is, the more stable its base is. So basically, what we're going to do here to predict the position of equilibrium, that's why I have this kind of open box here, so we're going to put in our arrow notation afterwards. We want to predict the position of equilibrium with no pK value or any quantitative data given. What we're going to do is we're going to compare the base and the conjugate base, so the base is on the left and right side of the reaction, and we're going to see which one's more stable. And what we have to recall is the more stable base is the one with the more acidic acid. So I know that doesn't really quite make sense when I'm trying to explain it, but hopefully this example will cover up any of these confusions and doubts. So, if we want to predict the position of equilibrium for an acid-base reaction with no data given to us, the first thing I like to do is label what my acid, my base, my conjugate acid, and conjugate base is. So if I look over here, I see the only difference is this lacks a hydrogen while this has a hydrogen. So since this lost a hydrogen to become that, this is my acid, which means that this has to be my conjugate base. And then I automatically know that this has to be my base and this has to be my conjugate acid. So now what we're going to do is we're going to look at the bases on both sides. So we're going to look at this and compare that to the conjugate base on the other side. So right over there. And now we're going to determine which one is more stable. And how we do that is we use our 4 factors that we learned in the previous video, the qualitative perspective. So notice I don't need to do any deprotonation because these have already lost their hydrogens. So this lost a hydrogen. When it had the hydrogen, it was this thing over here. And this lost a hydrogen. When it had its hydrogen, it was actually, sorry, my bad. So when this lost its hydrogen, it was originally this. And when this lost its hydrogen, originally it was that. So, yes. Now what we're going to do now is we're going to predict which one would be more stable by using our 4 factors, and it works in the exact same way. So just pretend like you were doing a question where it asked you which is more acidic, and use your factors. So your first step, deprotonation, which has already been done for you here because you've identified your 2 bases. And now what you're going to do is you're going to move on to the factors. Well, the first factor doesn't help me because the negative charge is both on the nitrogen atom in both cases. There's no inductive effects or orbitals, but I wouldn't even bother looking at those because the second thing on the list right after which atom bears the charge would be looking at resonance. And indeed, both of these do have resonance. So this has resonance over here. I'm not going to draw the proper notation. I guess I'll just draw the arrows. But since they both have resonance, what do I notice? Well, I notice that this is resonance stabilized over a sulfur atom. Well, this is resonance stabilized over an oxygen atom. And what we know is that the sulfur is a bigger atom than the oxygen, so it can better stabilize that negative charge. So I know therefore that this wins and that this is more well, I guess you could say the original compound would be more acidic, but this is the more stable base. And since this is the more stable base, what that tells us about equilibrium is that equilibrium always favors the production of the more stable base. So in this case, our equilibrium will favor the left hand side. So therefore, if I wanted to draw my curved arrows, I would draw this like this, and this shorter to indicate that. And that's basically how you do it. So when you're not given any quantitative data, what you do is you compare the bases on both sides and determine which one's more stable. And you determine which base is more stable by looking at the 4 factors that we had talked about previously. So That's that one. And now what I'd like to focus my attention on, since that was like kind of the last thing I wanted to cover for acids and bases, is the following question. For the following reaction below, draw the mechanism, draw the products, and predict the position of equilibrium. Now this is a question that you could most likely see on an exam, because this question covers pretty much everything we've talked about. What it'll cover is you knowing an understanding of the acid-base reaction mechanism, which is called a proton transfer. It tests your knowledge of knowing which side equilibrium favors. It tests your knowledge of being able to identify acids, bases, drawing products, conjugate acids, conjugate bases. And it also tests your ability to see if you can determine or come to a conclusion based off of the 4 factors from the qualitative perspective. So what I encourage you to do is to pause the video and try the example on your own, and then just unpause the video and work through this example with me. So the first thing I like to do when I see a question like this is I always like to label what. And just in case you guys are wondering what this box refers to, this box is essentially just the arrows and how we're going to put those in the end after we've determined the position of equilibrium. But for now, let's just focus on identifying our acids, our bases, our conjugate acids, conjugate bases, and stuff like that. So right now, I'm not given my products. So if I'm not given my products, the first thing I should do is I should first be able to understand what my base and what my acid will be. And from there, it'll be much easier to draw my conjugate acid and conjugate base. So what do I notice about these two? Well, I notice that this doesn't have a hydrogen. It's lacking one. That's why it has that negative formal charge on the oxygen. And I know that eventually one of the products, it will have a hydrogen. So one of the products will be the exact same, but it'll just have a hydrogen tacked onto it. So it'll be something like this. And what I also know is that in this case, for the acid-base reaction, this, since it already has a hydrogen, its product will have a hydrogen that's lost. So it'll get that negative formal charge over there. So those are what my 2 products will be. Now it's just a matter of identifying my acid base, my conjugate acid and conjugate bases. So if I look over here, from here I don't have a hydrogen and then I gain a hydrogen. Well, if I'm gaining a hydrogen, I know this has to be a base, which essentially means that this has to be my conjugate acid. And that automatically tells me that this has to be my acid, and this has to be my conjugate base. So now that we've determined that, I think we should draw the mechanism, because now we've identified our acid and base. It should be clear what the mechanism is. Remember, in acid-base reactions, the mechanism, were specifically called the proton transfer. The base abstracts a proton from the acid. So since this is a base, it'll abstract the proton from the acid, and that will kick off its electrons over there. So that's the mechanism that they're looking for. And now to predict the position of equilibrium, all we have to do, since we're not given any quantitative data like pK values, we're going to have to compare it with our quantitative perspective. So what I do here is I look at my base and my conjugate base, and I determine which is more stable by my 4 factors. So since this is my first base, I'm looking at this. Versus my conjugate base. Over there. And now I work through my 4 factors. Well, the first factor doesn't help us at all because the negative charge is on the oxygen, and it's also on the oxygen here. The second factor, resonance, doesn't help us either because this is resonance stabilized. If I showed the arrows like that, and I won't continue the notation, but I'm just kind of giving you an idea of what the resonance would be. And in both cases, the resonance is stabilized over the exact same atoms. So factor 2 doesn't help me at all. But what I notice is this has fluorine atoms. Remember, those halogens give us a good hint of inductive effects, and this doesn't. So this fluorine is the most electronegative. The partial positives, this carbon would be the partial positive, and my arrow notation would be radiating outwards like that. And since this doesn't have any inductive effects and this does, that automatically tells me that this is more acidic. Well, if I was comparing the acidity of the compounds, the original compound of this with the hydrogen would be more acidic. But in this case, for the reactions, for qualitative data, this is the more stable base. And since it's the more stable base and it's on the reactant side, I know that the equilibrium will favor the reactants, because it always favors the side with the more stable base. And in this case, it's the reactant. And how I do that is I draw a longer half arrow towards the reactant side and a shorter one toward the product side to indicate that that is the position of equilibrium. So that's kind of a question that can test all your knowledge, and I have one more example, which is pretty much similar, and we're going to do the exact same thing. So I also encourage you to pause the video and try the example out on your own, and then check back afterwards. So this example I'm going to kind of fly by through a lot quickly, but if you don't really quite understand, just replay the video, relook at what I was just talking about in the first example and stuff like that. But I'll try my best to fill you in on the details. So in this case, we're going to start off, so I know that eventually one of my products will have a hydrogen, because that's lacking one. So it'll, well, I don't really need to show the hydrogen, even though, okay, I guess I will show the hydrogen coming out there, even though I shouldn't. I'm just showing that for simplicity's sake, I guess, but in a regular structure, it would just be a benzene ring. I mean, an aromatic, my bad. Benzene has double bonds in the aromatic ring. So once again, this is not benzene. That was a mistake on my part, but just an aromatic compound. So hexane, cyclohexane, sorry, my bad. So that's a cyclohexane. Anyways, and now in this compound, we know we're going to lose that hydrogen. So there you go. Those are our products, and now it's just a matter of identifying our acids and bases. Since this is gaining, there's only difference is this has a proton, this doesn't. This means it gains one, so it's the base. This is the conjugate acid, which means this is our acid, and this is our conjugate base. The base abstracts the proton from the acid over there, just like that. So there should be a little dash here to show a bond, but they connected them, so I kind of just put the arrow starting from this little kind of space indicating that there is an OH bond right there. And then now we want to compare the two bases on both sides. So if I compare this base versus this base, I can automatically tell by a factor of 1 that this will be more stable because the negative is on the oxygen, which is more electronegative than the carbon, since they're in the same row. So if this is more stable, which is on the product side, I know that the equilibrium will favor the product side. So this half arrow should be longer than this one to show that the equilibrium is favored in the products. And I guess that wraps up my discussion for acids and bases, and in the next video I'm going to move on to nomenclature of alkanes and starting to talk about Newman projections and all that kind of fun stuff. So if you have any questions, concerns, comments, leave a comment down below, and thanks for watching.